Welcome back to the next installment of the EV fuel gauge project. Last I saw you was back in January when I designed the board and sent it off to China and got them back, and then I came back to Barcelona for the summer. And I got sidetracked by some other projects, but now we're ready to go and jump into the fuel gauge again. Please feed the YouTube algorithm by giving the video a like. If you want to see more like this, click subscribe and ring the bell to be notified of new videos. If you want to chip in on my expenses, I now have Patreon and YouTube memberships. And here's the board after I put the solder paste on and started building it up. Do you see any issues? Yeah, you do. The capacitors that I ended up with were incredibly the wrong size, and that's a problem when you're laying out a circuit board. You got to pick the right package for the part, and apparently I picked the wrong package. This one is just a little bit too big, and this one is hugely too big, and I had to stick it on here and this wire has come off. But in order to bring up this switching power supply, I had to play with this. Then the problem became these MOSFETs, this way of protecting and isolating each power supply, doesn't work. So I had to go hunting for a new solution. Let's take a look at what I found. So here's my criteria. Basically, I'm looking for something that I've discovered the industry calls an ideal diode. It's something that only lets current through one direction, but not backwards, and doesn't lose any of the voltage on its way through. That's the difference between a diode and an ideal diode. So I'm looking for something that will isolate multiple power supplies coming in and also has reverse current protection, because I never want power going backwards through part of the power supply that isn't actually being fed by an external power source. It needs to accept, for me, between 3.3 and 12 volts plus a little bit, because the voltage from the 12 volt bus in a car is normally around 13 to 14 volts. I need a very, very low voltage drop from input to output, because if I'm sending 3.3 volts to the board and the ESP32 needs 3.3 volts, there is not much a voltage to play with. I needed to have a small parts count. I needed to take up a small area on the board. I needed to be affordable in my overall design. If the perfect chip costs $50, then that's just not going to work. And it needs to be available. I've gone and looked at so many chips that the suppliers just have none. So let's go through the list. This is a combination of things I discovered, and I started asking the AI chatbots to help me out, and they gave me a lot of good information. So this first one is from TI, the LM73100 chip. Unfortunately, it's got a half a volt drop in voltage, and I can't go down to 2.8. It needs 7 passive devices. Some of them may be optional, I don't know. It's cheap at 63 cents. So this one is basically out because the voltage drop is too high. Next, I looked at the Renesas ISL6146. I think the problem on this one was it's just not available from any suppliers that I could find on the market. So I moved on to the ADI LTC4359. It's out because it has a minimum 4.0 volts coming in, and I need something that'll go down to 3.3. It's also quite expensive, but when you bump your quantities up, the price drops quite dramatically. The next one was an OnSemi NCP4681DSQ. This is still a possibility, but I had to look and see what else was on the market. It only has a 35 millivolt drop, so that's still, it could work. I went to the TI LM66200, only goes down to 5.5 volts. We're going to skip that one. the onsemi NIS6150. The voltage only goes up to 13.2 from the battery, so I don't want to take the chance of sending in 13.8, so that one's out. TI LM505 has a 5-volt input. The Vishay has a good low voltage drop, and a couple of the others, but the one I ended up going with is this one from Alpha and Omega Semiconductor, the AOZ for Alpha and Omega Z1390DI. There's an optional one. There's one that you have to manually unplug and plug back again if there's a fault. The other one will do a restart. The voltage range is great. The voltage drop is very small, so I'm happy with that. It reverse blocks, that's great. It only needs 4 capacitors and 1 resistor. It has a 14-pin extremely small package with a thermal pin underneath. It's $2.14 in quantities of 10, and that's okay. And I chose this, and I went ahead and ordered it from DigiKey, and to get free shipping, I just ordered some more ESP32s. And here's the spec sheet. It describes itself as an ideal diode, and it's designed for applications with multiple power supplies and ORing them together without causing any problems. 3.3 to 23 volts, and it's actually designed for multiple Type-C power delivery current inputs to a board. So this chip could literally not get any better than what I'm hoping for. I'm already taking care of this diode. It needs 4 caps and a pull-up resistor. So the amount of space it takes on the board is going to be very small. Okay, folks, this is it. The boards have come back from China. They look really good, although the main chip I'm trying to test is this little microscopic one right here, and I can't even focus on it because it's so small. But I'm working from the interactive bomb tool that the KiCad extension spits out. It automatically tells me. I hover over a part and it tells me where to put it on the board. Luckily, there's not a lot of parts. All right, they're all hand placed. Boy, I want an Opalo. I'm going to put a link to it here. It's a desktop pick and place machine that is just magic, and I really want one. I'm going to use my hot air gun and very carefully solder all these puppies down. All right, it's done. It's ugly, and it left a lot of little tiny solder balls, so I had to go around with the tip of my soldering iron and kind of touch them and melt them off because I don't want them rolling around getting stuck between pins. All right, now goes the connectors. Okay, there it is, connectors and a ground pin I can clip my meter to as I probe voltages around the board. I cleaned it up. It actually looks pretty good, but I'm not going to do anything more. I'm going to go to sleep, have a good sleep, and then double check everything in the morning. All right, here we are, the moment of truth. We're getting ready to test. So theoretically, I've got 12 volts coming in here, 5 volts coming in here, 3.3 volts coming in here. And this little chip, this guy, is the whole purpose in life of testing this board. So before I put any power to the board, I decided to test for shorts, and I found one. Look at this. This is obvious. This is my 5 volts coming into this power supply system. It goes straight to the ground pin. That is so dumb. And why did KiCad not catch that when I ran the signal test to make sure that the signal was going to the right thing? So I have to cut that and then put a little jumper wire in the back of my test board. I've got my power supply, which you can't see, set to 5 volts and limited to 100 milliamps, so hopefully nothing will catch on fire. Might just run a little hot if there's a problem. and I'm going to turn it on. 3, 2, 1. Okay, it's reading. Whoa, look at that. Things lit up. I'm at 5 volts, 80 milliamps, and we've got lights on the board. So let's check our voltages. 5 volts coming in is showing 5 volts. There is no fault. If there was a fault, this would light up. The output, I think, is on this cap. Yeah, 4.961 as opposed to 5.001. So 4.961, we're losing 40 thousandths of a volt as we come through this protection chip, which is awesome. I am not going to complain about that. If we look here, this is the voltage regulator input, which is also 4.961. The voltage regulator output is 3.268 out of this 3.3 volt regulator. That's down 32 thousandths of a volt from where it should be. So I'm going to call that a success. So we've got 3.3 volts coming out, and this is the final output of the whole system right here. Framing, we're at 3.231 as we go through this protection stage. So we're down 69 thousandths of a volt, and the ESP32 will happily run at that voltage. Now, I don't know why that's not lit up. Maybe I've got that soldered in backwards. That's a possibility. But what we've proved is 5 volts can come through here, perhaps protected, going through this switching power supply, highly efficient switching power supply, through the final bus protection, and we are at 3.231 volts. So I'm really happy about that. Let's try the 12 volt stage. I did a check, and it turns out that the limiting resistor to the LED was not connected to the power. Another dumb problem. KiCad, you're letting me down. You're not telling me things aren't connected. Anyway, so I've set it to 12 volts, 100 milliamps again, powering up. All right, we have 12 volts here. The LED fault light is almost lit up, but those ones look okay. We are reading 12.00 on the input. After the diodes, we're at 7.61, this whole protection diode section. The output of that is 7.57, so we lost 4 hundredths of a volt, which I'm okay with. Then we come in here, the input to the regulator, 7.57, the same as we're getting on the output. After the regulator, 3.26. After the last, coming into the bus protection stage, 3.26. And the output is 3.22. So again, lost 4 hundredths of a volt coming through the protection system. So that is all, that path is working. For those of you who don't know, the ESP Progue is the way for you to debug your software for an ESP32 chip running on a board like this. This comes as a serial port out of your computer. Through here, this circuit sends the debugging messages back and forth, and you get power and signals over this cable. This can either deliver 3.3 volts or 5 volts to your board, depending on which chip you're using. So I have the jumpers on the 3.3 volts, so we should be getting 3.3 volts on the output. So let's plug this puppy in. Oh, kind of looks okay, maybe. Let's go. Yeah, because this doesn't need to be regulated. So I don't need to send this on a path through the regulator circuit. Let's get a little more light. So we're getting on the output of the ESP Progue, we're getting 3.30 right on the nose. The output of the protection chip is 3.26. There's our 0.04 of a volt. No fault. Comes into the final bus. No, sorry, that comes out of there. And then the final output is 3.26. So all of the power stages are working independently. 2 of them are regulated, 1 is not. All 3 are buffered through this final stage. Now, the real test is going to be trying to do 2 at the same time, because that's the whole purpose in life of this chip. So cross your fingers. All right, 5 volts is hooked up, 5 volts dialed in on the power supply. We've got good voltage all the way to the end, as we would expect. Now, I'm going to plug the ESP Progue in. This should light up, but we should still see good, stable 3.3 volts here. Okay, we are now running 2 in parallel, and we're at 3.26 volts. They're not fighting, nothing's on fire, and we're getting exactly the voltage we were hoping for. Fantastic. All right, now I got to find myself a 12 volt power supply and plug it in here, and that will prove the entire system. Okay, this is the big test. I found a 12 volt little wall wart power supply that I had already sacrificed the connector on, so that's here. My bench power supply is here, set to 5 volts, and the ESP Progue is ready to go. So let's power these up in sequence. There's 12 volts. There's 5 volts. ESP Progue. We have all good lights, no fault lights. Power is coming through, and our final output is 3.26. We have happy, happy lights. That means this chip works and it does the job. And the key thing I was looking for is that it didn't have a huge voltage drop. We're losing 4/100ths of a volt, whereas you put a normal diode in here, you're losing 0.7 of a volt. And I can't handle that. I can't have my 3.3 go to 2.6. The ESP32 will never power up. But now I've got 3 independent power supplies protected from each other and regulated, going all out to a final protected power supply of 3.26 volts. So, people, this is the chip you want for multiple independent power supplies in parallel. Now, the way I designed the board was so that I had the ability to like cut traces and solder, so I gave myself a lot of room. I didn't need to have the LEDs here on the, the showing the faults. I didn't need all this other stuff. So when I designed the final board with this will take a much, much smaller space on the board. So I'm so happy I found this chip, because it's exactly the one that I want. All right, signing off for now. Next video will be hopefully a new one of these boards. This is the bad power supply right here. Will be replaced with these key components here. Before we wrap up, I'd like to thank my Patreons and YouTube members, Peter Bouvier, Puppy, and Craig, for their ongoing support. I see that a whopping 96% of my viewers are not subscribers, so please go ahead and click that subscribe button, because it really helps out the YouTube algorithm. Thanks, and take care, and I'll see you in the next video.